Okay, welcome to MA3002, Solid Mechanics and Vibrations. Let's get started. This is tutorial 1. I'll be going through principles of virtual displacement. So, what is principles of virtual displacement, or otherwise be known as PVD? So, in a typical problem, for a structure that is in static equilibrium, no work is being done. Okay, so in other words, the formula that we all know and love for PVD will be this, right? Delta W equals to 0. So many students just memorize this blindly, but there's actually a meaning to it. So I'll show you how it makes sense. So, sorry. For a structure in static equilibrium, no work is being done. We want to find a force that applied to keep the structure in equilibrium. Okay, so this formula should make sense. Think about it. The structure in these typical problems are in static equilibrium. And what does static equilibrium mean? Qualitatively, you can just think of it as not moving. Okay, so the structure is still, it's just rigid. It's not moving, so no work is being done. That makes sense, right? If you don't move anything, you don't create any displacement, so you don't do any work. Because we all know that work done is given by force dotted by displacement. Okay, hold on. Okay. So work done is force multiplied by displacement. So if the structure is not moving, you don't displace anything. So this is 0. And hence the work done is just 0. That's why we claim that the PVD formula is delta W equals to 0. It means the sum of the works done, yes, this is the sum of works done. All the works done, you total them up, is equal to 0. Because no work is being done in a static equilibrium condition. Right? It's just not moving, so no work is being done. Okay, now that we can make sense of delta W equals to 0. So, in these typical problems, what we want to find, right, is the force applied to keep the structure in static equilibrium. So let me draw you a simple structure. Let's say we have something like this. Okay, this thing is on a slider. This NA here is on a slider, so this can slide back and forth. And then let's say this joint here has a weight, so a weight of W. So, and here's pin jointed here. Okay, so this part is free to rotate, and also this part is also free to rotate, and also this part is free to slide back and forth here. Okay, so if I have this force W applied on this joint, what will happen? Intuitively, we know that it will just collapse downwards, like, right? It will just collapse downwards. So we don't want to have it collapse downwards. We just want it to be stuck like that in this V-shaped configuration. So what do? We need to apply a force over here. And most of the problems in PVD wants you to find this force. They want you to find this force to keep it balanced, to keep the structure in static equilibrium. So that's the objective of PVD. We want to find this force to keep this whole structure in balance. So what are the steps to doing PVD? So I outlined it all here. So step 1, first, you must assign the displacement coordinates to each force. So what does that mean? So let's use this structure that I've drawn here. So to do this, there is a special criteria that you need to do, that you need to satisfy to assign the displacement coordinates. You can't just simply assign it however you want. So what is that special criteria? You must start from a fixed point. Okay, emphasis on fixed point. Okay, fixed. This is important. And you stop until you, until you reach the force. So let us use this as an example. How do I assign the coordinates of, for example, let's start with F. So we have the forces F and W. Let's assign the coordinates to F. So we start from a fixed point. Now, in these diagrams for PVD, right, you can tell what's the fixed point by this shading. Yes, don't take this for granted. The shading actually means it's a giant wall or a floor or a ceiling. And for these problems, these ceilings, walls, and floors, they don't move. They're just a giant monolithic structure that just doesn't move. Okay, so whenever you see these hatched lines, like for example or this or this, the walls, the ceilings, the floors, these are indicating fixed structures. So since this is a fixed structure, we can start from this here, and then we draw our coordinate axis all the way until we reach the force F. You see? Now I've reached the force F. And then you must continue a little bit further with this. So let's just call this X. You can call it whatever you want. You can call it H, you can call it D, you can call it whatever you want, really. And then after you draw the coordinate axis, this one, you must draw an infinitesimal. So what is an infinitesimal? It's this here, delta X. So an infinitesimal is a very, 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 very tiny change in X. It's very tiny. It's in the limit as it approaches 0. But it's still not 0. Anyways, don't think too much about it. Just think of it as a small change in X. You displace X by a little bit, okay? So let us continue to find the coordinate axis, assign the coordinate axis of W. So how do you assign the coordinate axis of W? Again, you must start from a fixed point. Emphasis on fixed point. You never start from a moving structure. Okay? Oh yeah. So let me just emphasize what this means. This means not moving. Okay, I know it's obvious, but people tend to take this for granted. So I just want to emphasize it here. It's not moving. Okay, so now W seems tricky, right? Where is the fixed point that gets me straight from the fixed structure, which is this ceiling up here, until it reaches W? So what you do is, right, you can extend the wall yourself. So what do I mean? So they only show a small section of the wall. But in reality, right, you can actually extend this whole floor. I mean, this whole ceiling. Yeah. So what I mean is this. You can just extend it like this, continue the wall, and then you start from this fixed point now. See, you extended the fixed point. You've extended the fixed structure, which is this ceiling. And then now, from this ceiling, you can start from the fixed structure and then go all the way down to W. Okay, let's call this Y. And then you put the infinitesimal. So delta Y. Like that. So now you've assigned all the coordinates for both your force, F, and then the weight, W. Okay, so this is the way you assign your coordinate axis. I know in the tutorials throughout here, they assign it for you, but in the finals, I know some questions want you to do it yourself. So this is the idea. You start from a fixed point, and then you go all the way until you reach each force. Yeah, so that's how you do the coordinate axis. Okay, and then step 2 is you write out the formula. Now this formula, delta W equals 0. This means the sum of the forces. Oh, sorry, the sum of work done. Sorry, sum of work done. So how do you write this? You total up all the forces multiplied by the infinitesimals. So for example, in this example I have here, we have the force F assigned to the displacement delta X, and then the force W assigned to the displacement delta Y. So you see, it's the force multiplied by the infinitesimal, the force multiplied by the infinitesimal. And then you equate this all to 0. If there are more forces and more displacements, you just add them all together. Okay? So that's easy. Okay, so number 3, I guess, is the trickier bit. Express all coordinate system to a common variable using this. So if you don't know what's this is called the small approximate change formula. I've learned this when I was at O level, so I don't know about you guys if you remember this. I remember studying this in A math. Yeah, so small approximate change. It makes sense. So you see, this formula makes sense. If you want to find a small change in the value of y, what you can do is you approximate it by saying, hey, you take the derivative of y with respect to x, right? So dy dx. Then multiply by the small change in x. So you see, this isn't a good explanation, but here's one that helps you remember this formula. So you see, dy dx multiplied by a small change in x, what you can cheat yourself to think of is this dx cancels with this dx. See, leaving you dy, which gives you the small change in y. Okay, mathematicians are gonna kill me for saying that, but this is how you remember it. Okay, so okay, a little disclaimer. You have to find the formula. See, since you are taking a derivative of y with respect to x, so dy dx, you need to find the relationship between y and x. And here is where I warn you that you must be familiar with your geometry. So what kind of tools are important for your geometry here? So for example, trigonometry, your sine, your cosine, your tangent, your secant, your cosecant. I think those last few are seldom used, but yeah, I think the most important ones are like sine, cosine, tangent. Okay, so your trigonometry, and then what else is important? Pythagoras formula. So a squared plus b squared equals to c squared for a right angle triangle. And I guess sometimes we use the cosine rule. So if you don't remember, the cosine rule states a squared equals to b squared plus c squared minus 2bc cos a. Okay? So I'm not going to delve deep into here. Please recap this if you've forgotten. These are pretty secondary school stuff. And okay, so we move on to part 4. So drop the infinitesimals. This won't make sense here now. I'll show you what I mean later. And then solve for the applied force. So you make F the subject, right? We want to find the expression for F. So you make F the subject. That's what step 5 is about. So let us hop right in with an example. So in this question, what did it ask? We want to find F. Okay, so basically we want to find F. So let us start. Using PVD, right? So PVD states that, okay, let us start with by using this cookbook outline that I have here. So step 1, assign the coordinates to each force. It's already assigned for you. You see? This is started from the fixed structure. Actually, it is part of the fixed structure. If you extend this ceiling, right, you can extend this ceiling like this. So like that. So see, it starts on the fixed point and then it reaches the force W. Okay? So this is done. Then write out the PVD formula. So the PVD formula states this, the sum of work done is equal to 0. Okay. So who are the forces acting in our structure? See, we have first F and then W. So let's take a look at F first. So what is the work done by F? It is force, which is F, multiplied by the infinitesimal, okay? Not the coordinate axis, but the infinitesimal. So F multiplied by delta X. So first we have F multiplied by delta X plus who else? So we have W here. So what's the work done by W? Force times distance. So we have W multiplied by the infinitesimal delta Y. So W delta Y. And that's it. We only have 2 forces, so that's all our work done. So step 2 is done. Now, express all coordinate systems to a common variable using the small approximate change formula. So, how shall we do this? We have to take a look at the geometry of the structure. So let me clean this up for a bit. And let me just take a photo of this. That means we need to find ourselves, through the geometry of the structure, a formula that relates x to y, or y to x. It doesn't matter which way. So let me see how I can relate x to y. So taking a look at this structure, let us split this triangle over here. Okay, I'm focusing on this triangle right now. I'm gonna split it, and then let's call this part let's call this A, and this part called B. So I split X into A and B, right? So we can claim that, okay, so what I say is I let X equals to A plus B, right? So this is A plus B, which gives me X here. Okay, so I had to find what is A and what is B. So how do I find A and B? Focus on this triangle. Notice it's a right angle triangle, right? So in right angle triangle, we can use the Pythagoras theorem. So we know this side. Wait, let me say it. Okay. We know this side, which is L1, and we know this side. What is this side that is highlighted yellow here? This side is actually Y, right? It's actually Y. So we know that this is Y. And then since we know all three sides of the triangle, we can use the Pythagoras theorem. So we can claim that by Pythagoras theorem, L1 squared is equal to A squared plus Y squared. See, the square of the hypotenuse is given by A squared plus Y squared. Okay, I hope everyone can see that. This is a right angle triangle. So let's make A the subject here. So if you make A the subject, you can bring Y squared over, and then you move square to the other side, it becomes square root. So A is actually L1 squared minus Y squared. Similarly, if we focus our attention on this triangle over here, we can use the Pythagoras theorem and claim that L2 squared is equal to B squared plus Y squared. So making B the subject, you shall get B is equal to L2 squared minus Y squared, and you square root the whole thing. Okay? Now, I found A, I found B, I'm going to put them into my expression here. See, A plus B will give me X. So I shall sub these two, sub A and B into X. So remember, we let X equal to A plus B, and then A, we found out it is this expression here. So it is L1 squared minus Y squared plus, and then B is this expression here, L2 squared minus Y squared. So this is X. See, we effectively related X to Y. Look at this. This is X, and then we produce this formula, which contains Y. Do you see? Do you see Y inside? See, Y is over here, Y is over here. So we've managed to relate X to Y, and this is important throughout PVD. You're always going to be relating one displacement coordinate to another using the geometry of the structure. Okay, so this is the essential underlying concept behind PVD. So now that we found X in relation to Y, what's the next step? So this one's done. Drop the infinitesimal. Okay. Before we have to use this. Yeah, drop the infinitesimal. Sorry, not drop the infinitesimal. Sorry, we haven't done part 3 yet. So the common variable that I'm using here is Y. Sorry, is Y. Yeah. So how do we use this formula? Okay. So we need to find delta X. Okay, you'll see Y later. So to get delta X, we need to use the small approximate change formula, which is dx dy multiplied by delta y. Okay, I know the formula that I give you is delta y is equal to dy dx multiplied by delta x, but it doesn't matter, right? I just swap the order accordingly. So x goes to y, and then yeah, everything is in the correct order. See, x to y. I replace all the y's with the x, so it doesn't matter how you use the formula as long as it's consistent in its order. So x to y, and then all the x's are replaced with y, all the y's are replaced with x, and so on. Okay, so yes, I'm gonna use this formula. So what we are doing here, right? Using this formula, sorry, delta x equals to dx dy multiplied by delta y, is that we are trying to um we are trying to express the infinitesimal delta x as a function of delta y. See, we're trying to convert this into a version of delta y so that we can drop the infinitesimal later. So I'll show you what I mean. So first we need to find dx dy, right? We've already found an expression of x. Well, where does the expression of x come from? It comes from here, this. Okay, so let us find dx dy. So first let us find dx dy. dx dy is equal to d dy of this giant green highlighted expression here. Okay, so we need to differentiate this. So let me first write it as like this: L1 squared minus y squared to the power of half plus L2 squared minus y squared to the power of half. Okay, essentially I just changed the square roots to powers of half. Okay, so now I can do the derivative. So differentiate this with respect to y. So power bring down, power minus 1, multiplied by the differentiation of the insides. Okay, this is chain rule. You need to multiply the differentiation of the inside. So multiply by the differentiation of inside is minus 2y, right? Power bring down, power minus 1. Okay, plus, same with this, power bring down, power minus 1, and hold on, I need more space. Multiply by the differentiation of the inside, which is negative 2y. Okay, so if you simplify this, so this 2 and 2 can cancel, this 2 and 2 can cancel. What you're left with is negative y over root L1 squared minus y squared plus, yeah, just plus negative y L2 squared minus y squared. Okay, yeah, just like that. So essentially this power, this negative power I have, I bring it down to here. So this is dx dy. Now we put this dx dy. So let me just remind you, oops, sorry. Let me just remind you that this dx dy, we're gonna sub this into here. So that means